This is the mission 52, organized by Space Analog Station at Marte. And today we will have the presentation of Davi Souza about the sanitation center. Okay, just a moment. Okay, Davi, you are the host of the meeting, and now you can share your screen, okay, to the members of the mission. Okay.
All right. Just a moment. Tell me if you can see my screen.
Yes.
Okay. So, hello to everyone. I'm Davi Souza. Just to present myself, I am an electrical engineer student and also a research of Habitat Marte. I have been researching with Professor Julio more than a year, and some of these presentations are the result of this research that was conducted not only by me but with Professor Julio. And today I will be presenting about the sanitation center. And thank you for. It's a pleasure to be here, presenting and sharing this content with you. And thank you, Professor Julio, for to let me here and be presenting for the crew. So this is the topics that I will be explaining today. Some just to be really quick, some considerations about the design that I will be presenting a proposed concept by me. Some topics about the technologies, also the structure, the management of the structure. The other topics are more related to the protocols, and in the end of the presentation, I will be presenting more details about some spin-offs to be, and also technologies to be applied here on Earth. First of all, considering the internal design, we had this proposal from Yashihato in a previous mission of Habitat Marte. This is the concept proposed by him for an habitat on Mars surface. And as you can see here, we have the sanitation center. And I really like to, I always like to comment about the logistic position of each center when I'm presenting about the center. As you can see here, the sanitation center is closest from the engineer facility and the greenhouse facility too. So considering the logistic, I'll be presenting more details about it during the presentation. But just to be you have an idea, the idea of this location would be to make more feasible to conduct research and also other routines associated to water and technology and also crop cultivation. The visual concept of the Martian habitat, another just to show you the location of the sanitation center. And considering this internal design and this proposal from Yash, the idea is that the facilities is a circumference shape with 8 meters of diameters, and I will be considering the 3 floors for this facility. The basic characteristics is to provide a dormitory with beds for the astronauts, a kitchen and dining room, a toilet, and also have a food micro production. And here I'm not only considering the vertical gardening, but also the algae cultivation that I will be also explaining in the next slides. And for the whole facility, levels, the division of these 3 levels for the systems and also for the logistic inside of the facility. And we have the water management level, the wastewater treatment level, and also the recycling level. So the idea of the sanitation center is to integrate these three levels into one specific area, into one specific structure. The habitat design also proposed by Yash, and I for to locate each thing inside the facility. I'm proposing here in the ground floor. We would have the reservoirs, the algae cultivation, and also the laboratory. In the first floor, we will have the monitoring area and also the bioregenerative life support systems. And in the second floor would be more for living, it would be more a living space for social and entertainment, and also sleeping and toilet. And this is the division that I'm proposing for the internal area of this infrastructure. And I will be presenting more details for you. I will be starting from the second floor to the ground floor. Starting from the second floor, we would have the basic things: the kitchen, the dorms. I'm considering two dorms because I will be presenting the positions in the next slides during the presentation. One bathroom and also a social area, and in the middle we would have, in this specific area, we would have the HVAC. It's the heating, ventilation, and air conditioning system. And going to the first floor, we would have the bioregenerative life support systems, and just to propose here a brief concept. We would have some machinery for wastewater, also for urine and moisture recovery and crop waste processing. And associated with this crop waste processing, we would have an area designated to cultivate crops with vertical farming. We would have some green walls and also some vertical beds. And also in this floor, we would have the control area, and it would be also a monitoring desk, and it would be associated to the environmental control and life support system for the whole structure in the first floor. And going to the ground floor, we would have the lab in the middle area, and also the algae cultivation area, the reservoirs. I'm proposing here 3 decoupled reservoirs, 3 decoupled water tanks, in case of if we have any kind of contamination or something in one reservoir, the other ones would be safe. And the maintenance area, this would be also integrated with a lot of sensors. I'm putting here the water pipes. The right one would be to deliver the water for the engineering facility, the power station, and I'm not remembering the other one, but it's okay. And the other water pipes would be to deliver the water for specifically not only for the greenhouse that needs a big amount of water, but also for the main station. And this maintenance area would be in a specific area in case of any repairment, or if we have any problem with the pipes. And this area would have the tools and these things too. So related to the technologies now, just to present to you technology that I'm proposing in this design. We would have some decoupled reservoirs to avoid widespread contamination. We would have water quality monitoring system. This is one of the most important things associated to this facility. We would be monitoring the water in the habitat. And also the other feature associated to it, we would have the sewage and wastewater treatment systems. that would be doing the treatment of the water and recovering the water inside of the structure, and if necessary for the other structures. The idea is to integrate, is to implement closed loop systems in these structures, and some support technologies that would be helping in the tasks and activities conducted inside of the sanitation center. We would have some robotic arms if necessary, and also sensors, automated system associated with automated systems, automated pumps, and also system for monitoring these pumps and the water flow. And this is specifically to have a better data collection, like have the water storage status, detect some possible failures in the water flow, and also some reusing and recycling practices in the structure, and also associated to the water, to the systems that need water to work. We would have the bioregenerative life support systems, the BLSS, also the environmental control, the ECLSS, and the HVAC systems. And now, this is a thing that I'm presenting for the first time now, that as it's happening, the IAC, and I suppose that the crew members are participating. I have seen some papers, and this I will be presenting here two recent published papers in this Space Life Sciences Symposium. The first one is this design of hygiene module using closed gray water cycle for inside of the Lunaris analog station. And just through some considerations of this IGN module would be the gray water collection and its treatment and reuse, the integration of this kind of sustainable technologies in buildings, in specific structures, the water management data using flow meters. It's a kind of IoT approach. The gray water treatment, as I mentioned, but it will be also designated for cultivation as and will be delivered for recirculation systems. And it's also an interesting kind of study that I will be presenting more details what we are doing here in Habitat Marte related to it. The wastewater management, as you can see, the microfiltration system, and just to mention, we would have the integration of the crops. The crops would be a good choice for this filtration, and also algae cultivation. It's also some interesting topics, and other specific filters for the structure, and the closed loop system integration of bio-wastes and into bioenergy. So transforming this bio-waste into bioenergy, and this is also an interesting thing when we are considering not only the sanitation center, but I also consider this when I'm presenting about the greenhouse. It's necessary to have all possible alternatives, to use all the possible alternatives to transform into another resource. In this specific topic, we would have the bioenergy. Just to present you, this is a recent paper, as I mentioned. The presentation is also available until today. I also recommend for my crewmates. And this is the picture showing the construction, the integration of this structure is a container that will be it will be a specific container for this sanitation this sanitation module. And just to present you the plant of this structure, we would associate. They will be associating and also the gray water collection treatment, a gray water tank, and also the clean water for other water use. inside of the lunaris. And the other one that I bring here, that is another interesting paper. It's a new water management system for the ISS urine and condensate. And this paper presents new approaches for water management technologies to improve reliability and maintainability, and have less power consumption. This is interesting topics, interesting features that it's important to have integrated to the whole, to all of the technologies that we have in the Martian habitat, that we would have in the Martian habitat. Also, some water treatment strategies to reduce the inputs, the chemicals and energy necessary, and reduce also the outputs considering the wastes. And the idea of these systems is also to feed the BLSS, like, and this would be delivered, this water would be delivered for the algae and or bacteria biomass production. And it's also, they also present a proposal for this mix regeneration with efficient removal of contaminants in human urine. Just to present you the actual technologies for urine recovery inside of the International Space Station in this right picture, and also to present here the regenerative environment controlling life support system. And as I mentioned, it's important to have a closed loop system associated to this structure. Just to present some basic topics here, we would have the crew that will be producing the wastes and the urine, and we would have the urine recovery technology to be processing this urine and turning into potable water. It's also important to say that this system has an amount of like, I think this water can be a 98 or 97% treated and turning into potable. And this would be also a good water for astronaut showering and hand washing, shaving, and for other specific uses. And this would be also associated for the humidity, the suite of the astronauts that would have another specific system these resources into potable technology. Really important and necessary, mainly for the sanitation center, would be the algae cultivation. I really like to bring this kind of approach into my presentations, because the algae cultivation has a multi delivers. As you can see here, we would have the edible biomass, as you can see in this picture. This is a cereal bar made with spirulina that the astronauts also already eats inside of the ISS. Also the generation of biofuels. As I mentioned, all the possible alternatives to converting to other resources are welcome. Also the CO2 into O2 conversion, the gas exchange inside of the structure, and the effluent treatment that is associated, the main aspect associated for the sanitation center. And just here to present this picture here, just to have an idea about the many possibilities that NASA is considering for to integrate algae in space technologies, not only for the ISS, but also Moon and active on Mars after. And some interesting resource to be generated in situ or transported from Earth. I really like the idea. I found that this of modular photobioreactors that integrates the parabolic reflector and a light tube that is put in the middle of the structure, and this is a subterranean structure, and I consider it can be really useful. It also has a video. I put the link in the presentation, but I think this would be really useful in the case of Mars. We would have we won't use the areas of with this kind of approach, we will not use the area of the structure to cultivate algae, but we would have a specific area to do this kind of cultivation, to generate energy, to conduct wastewater treatment, water waste treatment, and other approaches associated to algae. And just to present this another picture, another photo showing the water recovering and management system inside of International Space Station. And I also mentioned here the in situ resource utilization, as we would be using the Martian regolith, the atmospheric components, and urine processing. I didn't bring for the presentation, but just so you have an idea, there is, considering for a lunar habitat, there is a study that they are studying the association of lunar regolith with some components of the urine to transform into a raw material for a lunar habitat to be 3D printed, and it could be also useful for Mars in the case of Mars. So these are some interesting approaches that will make the life of future astronauts on Mars easier, I believe. Associated to the management of the sanitation center, we would have the organizational structure with 2 permanent vacancies. As I mentioned, we would have 2 dorms, the BM and the BF. I will be presenting them in the next slide, and a rotating vacancy that will be a visiting assistant. The idea of this vacancy, it would be filled in a rotating basis with the other members of the mission of the habitat. And the objective of this vacancy is to provide the minimum knowledge associated to the 3 levels that I mentioned in the beginning of the presentation: the water management, the wastewater treatment, and the recycling. And another interesting approach would be to encourage new practice among the astronauts, the co-creation practice, to improve the crew's mental health, not to allow that the other astronauts won't be doing always in a specific task and a specific routine, and they would have a mutual exchange tasks. And as I mentioned, we would have the 2 permanent positions: the bio manager, the BM, and the bio chief, the BF. And the bio manager would be responsible to conduct the good practices and awareness focused on the water systems, like the water distribution, and to conduct the monitoring and maintenance schedules. Would be more the general tasks associated to the management of the water. And the bio chief would be the professional that will conduct specific activities, like the installation of equipment and maintenance of equipment, and coordinate the experiments. And the idea is that this position would be integrated of the head of the laboratory that will conduct the experiments. It's also interesting that to say that these positions, it's necessary the minimal knowledge and experience on water systems, And this is more related to the chief of the structure. I propose that the disposition of the chief could be switched between the both permanent vacancies, the both permanent positions, and the chief would be conducting some meetings with the chief of other infrastructures. And just to give here some ideas of the backgrounds for these positions, we would have an environmental manager or engineer, an hydraulic engineer, a hydraulic engineer, a chemical engineer, or a biologist or biotechnologist too. And related to the visiting assistant, as I mentioned, would be a rotating vacancy. That would be filled for engineers, geologists, astrobiologists, and other specialists inside of the habitat. And it would be also responsible. The idea of the visiting assistant is also to conduct some specific experiments of their facility, of their specific facility, associated to water nexus. Like we would bring like the greenhouse chief to conduct any kind of specific research during a period inside of the sanitation center, and also like to associate it to water deliver and to have an optimal water deliver for the crops, for example, or the engineers or the other facilities. And just show some features incorporated for the astronaut training program. The idea is to have a sustainable human presence in space and conduct activities on the maintenance and have a sustainable operation of the whole habitat. Also to support long-term effects of isolation. This training would be, as I mentioned, one specific topic would be the well-being associated for the well-being of astronauts, and also providing new mental stimulus. And would be also associated for capabilities to handle the architectures and the technologies for human explorations, especially the BLSS inside of the structures, and also practice to reduce costs and technical risks in the systems, meeting for decision making, and other skills based on the situations identified at Mars, and also conduct some simulations. Some risks, conduct some eventual risks or something like that. The videos that I mentioned, just to be really quick, this is a video associated to algae for use it on the wastewater treatment process. Another video related to microalgae on the wastewater treatment. Also, some basic guidelines on reduce, reuse, and recycling practices. This is also for a good video for kids. And this is another video by NASA that's showing the water recycling in the ISS. Associated to the resource needed for 1 week, considering 2 astronauts, and just a moment. Associated to the food, it's necessary to say that the daily consumption per astronauts could be different from each astronaut. We will need to consider the weight, the height, the height, and the biotype and routines of each individual. And here I'm considering an amount of 2.1 kilograms per person, and making the calculus here for a week inside of the sanitation center, we would have an amount of 40 kilograms, and associated to water, I consider the 3 liters of water by person, as we have here on Earth, as the rate here on Earth, and it will be a consumption of 42 liters of water. This I'm considering the drinkable water, but we can. I didn't consider the other specific activities inside of the structure, and I can have this parameter for now. The guidelines for the water facilities would be the development of protocols and routines associated to water management for applied in each facility. So we would have specialized routines and protocols for each facility associated to the water, regular and extensive research to improve the water processes and technologies. For example, the development of more efficient water pumps, provide a clean and potable water, some indicators of consumption and control of water use, economy and recycling practice to be added in astronauts' routines, and other basic guidelines and training for handling and preventive maintenance of the water-related systems. The protocols now in this facility, specifically, we would have some monitoring routines, conduct the tasks on water management, as I mentioned before, and the idea is to all these tasks would have a reduced workload and also an optimal performance for the to improve the astronaut performance, and also to perform some preventive maintenance of the whole systems and technologies and equipments inside of the structure, and also here to preserve the conditions of the pipes. This is also important to don't have any kind of water losses. And also collect the reports from the other stations and compare with the data collected by the sensors. Protocols for safety, we would have, I'm proposing here the development. This is just a brief overview about how would be each protocol, but I'm considering here 4 protocols associated to safety. We would have fast isolation, just to analyze the available resource and see if we consider the approach of our mission that we are isolated due to a contamination inside of the habitat. This would be interesting to have an idea of the amount of resource that we have, not only food, but water and other resource in our structure. Some evacuation guidelines, and the idea is to optimize the water distribution in this case of evacuation, like to deliver the water of a specific facility if necessary, if there are any kind of other procedure. This would be also associated to the protocol to keep reliability. The rationing order is also some guidelines to avoid the water spreading of the water, to avoid some losses associated to the water, some unnecessary losses associated to the water, and also to keep the reliability is more it's more associated to monitoring and tabulate the response of the systems when we deal with emergency situations, and see the inventory of losses and also the recovery schedule if it's possible, and identify other critical points of the structure and tabulate the whole collected data. Some protocols for occupancy and entertainment. I'm proposing here basic guidelines associated to socialization practice, recreational moments, relaxing areas, and also the operational activities involving the plants, the interaction with plants, the preparation of food. I also was reading a paper of the IEC associated to well-being ISS in Antarctica, and it's also an interesting topic of research that I'm really inside of this topic. Associated to microproduction of food, just to present the picture here, we would have the vertical garden, and if it's possible, we would have like a minimal photobioreactor to have some algae cultivation only designated for food, for biomass, consumable biomass. We would have the food logistics, the risk management, and avoid losses associated to the crops. The monitoring reports that this would be delivered for the greenhouse chief, and also the waste management. And these protocols, this is a proposal made by me of my presentation, for my presentation about the greenhouse, and also I put this in the paper of the IAC made by me and Professor Julio, associated to agriculture in Mars. And this would be a basic guidelines proposed by the greenhouse. And the idea is to take these guidelines from the greenhouse and integrate in the other structures. And this would be associated to the routines of management, maintenance, recycling practice, and also harvesting and processing. And some activities on analysis, diagnosis, ensure circularity, ensure the fidelity of methodologies, and also have some orientations and detect possible failures. And this is another interesting topic related to the 3D printing. I was looking for I was wondering for a kind of 3D printing specific structure that would be useful, and not only specific tools or maybe the water pipes. This could be, I think this could be also a choice, a possibility, but this is an interesting approach that would be the development of photobioreactors using 3D printing, as you can see here. And this would be really necessary. As I mentioned, how important would be the use of algae. And to finish my presentation, the spin-offs, I will be presenting here the routines and practices implemented in Habitat Marte. And these are some technologies and outputs that we are applying here on Earth. So some practice, some activities on water analysis, as you can see in the left top picture. Also water recovering, this is also water we use. This is Dalmo, that is a aquaponics specialist of Habitat Marte. And this is a kind of practice of taking this water after the cleaning of the grow beds, the growing beds. And this water is put 30 days in a closed space, and this would have like a microorganical process that will turn this organic waste into nutrients for the plants, and this would be also reinserted inside of the fish tank of the aquaponic system, and we would have like a pump of nutrients for the crops. This is also a good practice on it. And another interesting practice and experiment proposed by Professor Julio in a previous mission, presential mission, is the use of the roots of the crops that we take off from the system. That in some cases we have some crops that is not producing anymore, and we need to take off from the system. And the idea is to use these roots as a substrate for we have two aquaponic systems. The one of them is the grow bed, as you can see in this cleaning activity, and the other one is the agriculture system that we have some net cups, and we put these roots inside of the net cups to have the substrate for the crops. And it's also interesting to mention that the roots has an amount of organic matter that would be also necessary, would be also useful for reusing. And other technology implemented in Habitat Marte, it's called Biomars, is a waste water treatment plant. We collect the water from the bathroom, and also from the kitchen of Habitat Marte. And the idea is to turn this water, like to have a process of treatment here to deliver this water for the cultivation of crops inside of the greenhouse. And some other guidelines to be applied on our daily lives here on Earth would be the water consumption management, the water saving and economic practices. This would be interesting to sustain life, support hygiene, and also have some investments in research aimed on waterways systems. As I mentioned, as I presented the two papers of the ISC, it's some new research in this specific topic, and this would be applied specifically in areas with low water availability. Just to mention the case of Habitat Marte, we are, Professor Julia already presented to you, we are located in a really dry area affected by drought, and we don't have the water availability during the whole year. We have also high temperatures that increase the evapotranspiration rates of this water, and so this kind of systems would be is really necessary in these places, in these areas of the globe. And related to the SDGs, Sustainable Development Goals, we would have some initiatives on economic growth, reduce, reuse, and recycling, and also the development of systems that use less water. I am presenting here in this picture the water resource recovery facility. That is a facility that integrates not only the water management, the energy generation, but also inside of a health environment, we would have associated the some IoT systems for monitoring and also for automation and control of this facility. And just to associate here with some SDGs, we would have the SDG 1, the SDG 6. This is the main SDG associated to the sanitation center. And the outcomes of these presentations, the topics that I have explained, also are correlated with the SDG 8, SDG 10, and also the SDG 11. And I really like it to mention the SDG 16, associated to peace and justice, is that we already know that there are some perspectives that consider that the next world war would be related to water. And so if we consider this kind of technologies, of solutions, would be a nice solution to avoid this kind of war that is really bad for our globe, for the humanity. So these are my reference, and thank you very much for your attention. I'm open for questions, comments, suggestions, and thank you again, Crew.